At this point, we're going to turn our attention to what's called conformation. Now, so far, up until this point in the course, what we've been doing is drawing lots of molecules, and they look static. So we draw the picture of the molecule or the ion or whatever it is, and it just sits there on the page. There's no movement associated with it. But that's actually not true when we think about the structures of these molecules. They can adopt what are called different conformations. And the conformations of a molecule, as it says here, are describing the different spatial arrangements of atoms that you get when you rotate around one or more single bonds in the molecule. We're going to be looking at conformational analysis, which is the broad term for what we're doing here, of both acyclic molecules, that is, molecules that are not rings, as well as cyclic ones. We're going to start by defining something that we call the barrier to rotation. So the barrier to rotation is the amount of energy that you have to put into that molecule to rotate around a particular bond. So it's the amount of energy required to rotate around a particular bond. So let's consider this in the context of a pair of sp3 hybrid carbons. So if you're an sp3 hybridized carbon, then you have 4 sp3 orbitals. So let's just look at the picture that valence bond theory would give us of those two carbons bonding to each other. Each would be using an sp3 orbital with a single electron in it. And so those orbitals would overlap between the two carbon nuclei in that fashion. Now, because this is a sigma bond, the bond density is along the internuclear axis. And so you can rotate around that bond without disrupting the bond. So rotating around single bonds does not disrupt the overlap of the orbitals involved in the bond. What we know about single bonds is that the energy required to rotate around them is typically not that much. So we can say, and we'll look at numbers in a minute, that single bonds have relatively low barriers to rotation. So low rotational barriers, meaning that they only require a small amount of energy to rotate. By contrast, if we think about a pi bond, so with a pi bond, what you have going on is a pair of p orbitals, one on each, let's say, carbon atom. Okay, so maybe you have a C here and a C here, and they're overlapping in a side-to-side fashion on either side of the internuclear axis, which is this line right here. If you tried rotating around that bond, the side-to-side overlap of the p orbitals would be disrupted. So rotation, I'm going to put it in quotation marks because it really can't happen, around a pi bond would destroy the overlap of the two participating p orbitals and therefore would break the bond. So in this case, The barrier to rotation is going to be a lot higher. The barrier to rotation here is going to be along the lines of 60 to 65 kilocalories per mole. That's the energy of the pi bond. So this discussion is to explain why we only look at the rotation around single bonds. So pi bonds we do not rotate around because in order to do so, you'd have to break the bond. Let's talk about something called torsion angles and Newman projections. So up at the top of this page, you've got a couple of pictures that look extremely geometrical and complicated, but they're really not that bad. So what we're calling the torsion angle, and also in chemistry it's referred to as the dihedral angle, so those terms mean the same thing here. The torsion angle is an angle between two planes. So that's shown in this picture on the left. And so you have two planes, and then I've just highlighted the angle between them, sort of. In chemistry, when you're contemplating a conformational analysis, what you're doing is inspecting a particular bond, and you're looking at what's attached to that bond at both of the carbon atoms involved in the bond. So let's say that the bond that you're concerned with in the picture on the right is the one that I've just labeled with C's. So you have a group coming off of the carbon on the left. Let's just call that group A. And you have a group coming off of the carbon on the right, and we'll call that B. So the torsion angle involves the angle between the AC bond and this BC bond. So it's still the angle between two planes. The two planes are shown by the shaded blue and brown areas. Notice that both of the planes include the bond that you're inspecting or analyzing, the carbon-carbon bond. So essentially what this comes down to is the angle between this bond and this bond. Now, in order to show this, we're going to use a particular notation that's called a Newman projection. So we're going to start learning to draw Newman projections now, but in order to do that, we need to now break out the models and see exactly what it means to do a conformational analysis. What is it exactly that we're doing? Now, for starters, we are looking down a bond. So that's the terminology that you'll hear. You're going to look down a bond. That means that you select a carbon-carbon bond in the molecule and you orient it so that you're sighting down that bond. Okay, so let's take a look. Whoa, nobody expected that. Okay, so here's a molecule. This is ethane. Okay, so in my hands are the carbon atoms, and then all of these guys are the hydrogens. Okay, so when I orient the molecule, notice that there's just the one carbon-carbon bond in the molecule. If I orient the molecule this way, then now from your point of view and mine, you can't see that bond. You're looking down that bond. When we look down a bond, we always describe the carbons in the bond in the following manner. So the one that's in my hand that's closest to you would be called the front carbon from your perspective. And now the one that I'm holding is the back carbon. So you have a front carbon and a back carbon in the bond that you're looking down. So that's always going to be the case, and we're going to show that in the Newman projection. Now, if we imagine rotating around this bond, that's going to look something like this. Okay, so this is rotating around the bond. And all of these other single bonds, by the way, are also rotating, but we don't care about that at the moment. We're just looking at the carbon-carbon bond. If you imagine rotating around this bond, if I do this in really small increments, okay, so we'll start here, and then I'm just going to rotate in very small increments, and notice how the spatial arrangement, the relationship of the groups that are attached to the front carbon, the relationship of those groups with the groups on the back carbon changes every time I move around the bond like so. Okay, so you have a very, very large number of possible conformations. But in practice, we're really just looking at a couple of major types of conformation. And that's what we're going to look at now. So we're going to start here. This is the case where all the bonds on the front carbon, all the bonds coming off of the front carbon, are directly in front of bonds coming off of the back carbon. Okay, so the front bonds eclipse the back bonds. And so we call that an eclipsed conformation. So we're going to draw this, but what I'd like you to notice is that on this front carbon, we have a red hydrogen that's pointing straight up. And on the back carbon, there's a green hydrogen that's pointing straight up behind it. What we're going to do is track the relationship of the bond to the red carbon with the bond to the the bond to the red hydrogen with the bond to the green hydrogen. So let's draw what we are talking about. Okay, so here's our eclipsed conformation and what we had on the front carbon. So in a Newman projection, the front carbon is represented by this point right here. So this is our front carbon. And so you can see 3 bonds coming off of it. The circle is the back carbon. And you can see it also has 3 bonds coming off of it. So what we just saw was that this H up at the top was the red one, and directly behind it was the green hydrogen. And then let's just go ahead and label the rest of these hydrogens with H's. Now in a Newman projection, unlike in a skeletal formula, you have to draw what's on the ends of the bonds. You can't just leave them blank and assume that someone will think that that's a methyl group. It may or may not be. So everything has to be written explicitly at the end of the bond. Even if you abbreviate it, you have to put something there so that we know, is this a hydrogen? Is this CH3? What is this? Notice also that when I showed you the model, this bond here was directly in front of this bond here. But we can't draw that in a Newman projection because we can't draw a line behind another line. So what that means is that you have to offset the line on the back carbon and just put it slightly to the right or to the left of the bond coming off of the front carbon. So when we think about the torsion angle between the bond to HR and the bond to HG, we recognize that it's 0. So the torsion angle between the C-HR bond, so front carbon, red hydrogen bond, and the C-HG bond, so back carbon, green hydrogen, is 0 degrees. And so what we would say about that is that the red hydrogen and the green hydrogen are eclipsed. So that's the term we would use for that relationship. Okay, let's look at continuing this. Okay, so a minute ago, what I told you was that although we have a very, very large number of conformations based on the many, many, many incremental moves we can make around the bond, we're really just looking at the major ones. So one of the major ones is an eclipse conformation. Instead of rotating in small increments, what we do is we rotate around the bond in 60-degree increments. Now, when you do this, the first thing is it's going to look something like this. Okay, so a 60-degree rotation is going to give you this structure. Okay? A second 60-degree rotation is going to return you to an eclipsed conformation. A third 60-degree rotation gets you back to this sort of a picture. And then you can continue that all the way around the bond until you get back to where you started. So again, we start with an eclipsed conformation. If we rotate 60 degrees, what we have is called a staggered conformation. Okay, now we're going to draw this in a second, but before we do that, I'd like to point something else out. What you might have noticed is that I kept the groups that were on the front carbon exactly the way they were, and I just rotated the back. And once I started rotating it, I rotated it and I continued in the same direction. Okay, whether that was clockwise or counterclockwise, I'm a little confused now because I'm It's kind of like I'm looking into a mirror. But the point is, when you start the rotation in a particular direction, you want to continue in that direction until you've completed the entire rotation around the bond. The other thing is, it doesn't matter if you rotate the groups on the back carbon, which is what I did initially, or the groups on the front carbon, because you're going to end up finding the same relationships, whether you rotate the groups on the back or the groups on the front. The thing is to be consistent. So if you start out by rotating the back groups, continue to rotate the back groups. If you start by rotating the front groups, continue to rotate the front groups. And remember, always continue in the same direction. Okay, so again, we started here, eclipse conformation. And so now we're going to rotate. We're going to do a 60-degree rotation to access a staggered conformation. So in a staggered conformation, unlike an eclipse conformation, the bonds are offset. So a bond on the front is offset by 60 degrees, to a bond on the back. So this one and this one are 60 degrees apart from each other. This bond and this bond are 60 degrees apart from each other. This front bond is 60 degrees away from this back bond, and so on. So that's a staggered conformation. Okay, so take a look at this model, and then we're going to draw what we see. Okay, so we kept the front groups in the same positions. So HR is still pointing straight up from our point of view, or from your point of view watching the video. And then we rotated the back groups. And when we did that, we ended up with HG right over here. The torsion angle between the bond to HR from the front carbon and the bond to HG from the back carbon, remember we rotated just 60 degrees, so this is now a 60-degree torsion angle. And so a torsion angle between the HR bond and the HG bond being 60 degrees, we would say that HR and HG are gauche. So a gauche relationship between two groups is a particular pattern that occurs in a staggered conformation. Okay, so over here on the right, though, we have another additional staggered conformation. Let's look at how we got to that, or how we will get to that, because we're going to come back here and draw it in just a second. Okay, so this is where we are now. So if we continue rotating the back groups, okay, here is another eclipse conformation. And we rotate another 60 degrees, and now we've got this guy. Okay, this is also a staggered conformation, but it's going to have a different name. So let's go ahead and draw what we see now and figure out what the name is. Okay, so the bond to HR still points straight up. But what we've done is rotate to the point where the bond to HG coming off of the back carbon is now completely opposite the bond to HR. So in this instance, the torsion angle between those two bonds is now 180 degrees. So the torsion angle between the front carbon and HR and the back carbon and HG is 180 degrees. And so we would say that HR and HG are what is called anti. To understand what's going on in the conformations that we're going to look at, we need to first understand a term called strain. Now, strain relates to something that you've seen before in general chemistry. So you might recall the delta H of combustion, or the enthalpy of combustion. Strain is a difference between two heats of combustion. So it's a delta H, if you will. So a difference between two delta H values. Okay, so what are those delta H values? Well, one of them is an actual value. It's a measured or experimental value. So we take a molecule and we combust it. So we take a sample of it, we put it into a contraption called a bomb calorimeter, which you're able to seal up. There's a wire that comes out of this. You can light that. It's like a fuse. You can light it. It ignites the sample within the chamber. The sample combusts. There's a thermometer. You can measure the temperature change. You know how many moles of the compound you put in. And from these pieces of information and other things, you can calculate what the heat of combustion is. Okay, so that would be an actual heat of combustion, a measured or experimental value. So you actually do the experiment and find out what the heat of combustion is. From that, you're going to subtract a theoretical heat of combustion. And this is going to give you your strain energy. Okay, so what's the theoretical heat of combustion? That's going to be a calculated version. So you're going to go to the computer and you're going to calculate a heat of combustion based on the assumptions that you put into the program that you're using to do this calculation. And the assumptions are going to be that the molecule has no strain. And so it's going to give you a heat of combustion that's based on a hypothetical version of the molecule that's strain-free. So what we can say about strain is that it's a difference in energy between a measured heat of combustion so a measured delta H of combustion for a molecule and a hypothetical calculated version of the heat of combustion for a strain-free version of that same molecule. So a theoretical delta H for a hypothetical strain-free version of the molecule. Okay, so there's programs that will do this. You just put in the parameters, you minimize energies, and it does the calculation for you. Okay, so what kinds of strain are there? There's three kinds of strain, and so we're going to talk about those now and then start looking at some examples of conformational analysis so that we can learn to recognize them. Angle strain. Angle strain is found in rings, which we call cyclic molecules. So any molecule that contains a ring may or may not have angle strain. What it is a deviation from an accepted or an ideal bond angle, and that depends on the hybridization of the central atom in the bond. So let's write that out and then think about what that means. So it's a deviation, and the deviation can be either positive or negative from an accepted or ideal bond angle given the hybridization of the central atom in that bond. Okay, so accepted and ideal bond angles. Well, you know these. For example, for an sp3 carbon atom, the ideal bond angles, or the typical bond angles around such a carbon, are going to be 109.5. So if you have an sp3 carbon and the bond angle around it is only, let's say, 90, that's a fairly significant deviation from 109.5 degrees. And so that would constitute an example of angle strain. So an example would be a 90-degree bond angle instead of the expected 109.5 degree bond angle around an sp3 carbon. So we'll be seeing that once we get into rings in the second half of the packet. The next type of strain we'll see in both rings and things that are not rings, and that's called torsional strain. So let me define what this is for you, and then we're going to take a look at this picture and look at some other things. So in torsional strain, what's going on is the following. Bonding electrons, that is, electrons that are in bonds, get too close to one another. And when electrons get too close, we know that what happens is that because they have the same charge, they repel, and that resulting repulsion raises the energy of the conformation that it's occurring in. So bonding electrons get too close to one another. They consequently repel, and this repulsion raises the energy of the conformation. The picture on the left, the photograph on the left, is very, very similar to the model that we were just looking at on the previous pages, and it's ethane. Okay, so you have two carbon atoms. I'm just going to number them. Here's 1 and here's 2. And let's draw this so that we know exactly what's going on. So we have 3 bonds in the plane, like so. And so these hydrogens are the yellow hydrogens. On the carbon on the left that I've labeled as number 1, there's a bond extending toward you, and that's to the green hydrogen. On the carbon on the right, the bond extending toward you, it's a little bit hard to see the color in the photograph, but that's a blue hydrogen. Also on the carbon on the right, the bond going back is to the red hydrogen. So I'll just call that HR. And on the carbon on the left, the bond going back is to an orange hydrogen. So that's HO. So here HO and HR. Okay, so this is a picture of the photograph. It's a drawing of the photograph. So this is eclipsed ethane. So this is ethane in its eclipsed conformation. And so remember, when you have an eclipsed conformation, as you're looking down a bond, the bonds coming off of the front carbon are directly in front of the bonds coming off of the back carbon. They're eclipsing them. So you can't see the bonds on the back carbon. So we turned it to the side, and this is what it would look like. So where the torsional strain is occurring is in the following locations. Remember that each of these sticks represents a bond. Well, after what we saw in packet 2, we now understand that these sticks are not very good representations of what the bonds really look like. That the bonds are really more like clouds of electron density. So for example, you might have a cloud here and then a cloud over here. And so it's this area in between those two bonds where the torsional strain is occurring. And that's true for each pair of eclipsing bonds in this system. So the two yellow hydrogens, the bond to the green hydrogen with the bond to the blue hydrogen, there's torsional strain there as well, so in this region. And then the bond between the orange hydrogen, or the bond to the orange hydrogen and the bond to the red hydrogen, those are also eclipsing. And so although I can't draw it on this picture, you're going to have torsional strain occurring there as well. The eclipse conformation is the only conformation where the bonds can align closely enough that the bonding electrons are too close to one another. Now, by bonding electrons, I'm just talking about the electrons that are in each of these bonds. So, torsional strain only occurs in eclipsed conformations. And further, every eclipsed conformation has torsional strain, because in every eclipsed conformation, bonds are lined up in this way, and so the electron clouds in those bonds, front and back, are too close, causing this repulsion. So every eclipsed conformation has torsional strain. The third type of strain that we're going to encounter is called steric strain. Now, steric strain is also known as van der Waals strain. So you're probably familiar with the term van der Waals forces, which is kind of a catch-all term for intermolecular forces. And from that, you may also remember that when you bring two molecules together, at a certain point, there are weak attractive forces that can exist between the two molecules. And those weak attractive forces give rise to what we would think of as the intermolecular forces. So things like dipole-dipole interactions, dipole-induced dipole interactions, London dispersion forces, and so on. But you also remember that if you start getting things too close to one another, that's when repulsions start occurring because of the electron clouds in one group repelling the electron clouds in the other group. So the same thing can happen within molecules. So what we have here is a picture, this time of propane. So I'm just going to number carbons from left to right, 1, 2, and 3. And so what we're looking at is what's going on with this hydrogen and the hydrogens on this orange methyl group at carbon 3. The steric strain exists right here. These hydrogens are too close to one another in this conformation of the molecule. This also happens to be an eclipsed conformation, but steric strain can happen in both eclipsed and staggered conformations. So let's write a definition of this. Steric strain we would think of as being atoms that are not directly bonded to each other, so they're not directly bonded to each other, but they're still in the same molecule. Get too close in certain conformations. Their electron clouds repel. And the repulsion raises the energy of the conformation. Now it's important to notice here that steric strain can occur in both staggered and eclipsed conformations. So we're going to take this information in the next video and apply it to a conformational analysis of ethane, and then we'll move along from there.